This is the last part of chapter 4, I promise, and this is about solution stoichiometry. So once you know how to calculate the concentration of a solution, which is molarity, now you can do solution stoichiometry, which is like the solid stoichiometry in which you were converting grams to moles and doing mole ratio, etc. Now you will be working with solutions. So, and now in this case, you will have the moles per liter to work with, and then you will still do the mole ratio and all that. That is stoichiometry. So that's what this chapter is all about. Now this is a little bit big because solution stoichiometry comprises of many different kinds. It's acid-base reactions, precipitation reactions, and redox. Okay, so it's a little bit big. Take your time when you do this. The next aspect of solutions is solution stoichiometry. So what we've done in chapter 3 was solid stoichiometry, where you were dealing with grams. Now we are going into solution stoichiometry, which means you'll be dealing with molarities. The nice thing about dealing with molarities is that you already have the moles calculated. In case of grams, you actually have to convert it into moles first. But the other aspect of solution stoichiometry is that you have to deal with solutions, which means you also have water in there. Okay, so you have to be careful. But anyhow, a little bit about what solution stoichiometry is that you still do the same kind of calculations, which means that you still have to use mole ratios, you still have to write equations, okay, for all the reactions because of the mole ratios. If you don't have a balanced equation, or if you don't know what the mole ratio is, then your solution stoichiometry is not going to work out, okay? So there are 3 kinds of stoichiometric calculations that we do. One is called quantitative, and in this case, you're just trying to determine the amount of substance you have in a material, okay, or any kind of a solution. The second one is volumetric analysis, and this is based on titration. And titration is a very common technique that you use for determining the unknown concentration or amount of solute in a solution. And in this case, you will use things like burettes and pipettes. And once you do the titration, you can find out the unknown concentration. In the case of volumetric analysis, you can do any kind of titration. So for example, you can do acid-base titration, you can do precipitation titration, you can do oxidation reduction titration. Those were the 3 reactions we've learned in solutions, okay, or in aqueous solutions. So you can do any of those 3 kind of titrations in volumetric analysis. So it makes it a very versatile technique. The third kind of technique that we use is gravimetric analysis, and gravimetric analysis is used specifically for precipitation reactions. And in case of precipitation reactions, you form a precipitate as a product, and that precipitate is isolated and weighed, and then you do a back calculation to figure out how much of that substance was actually in the solution. Okay, and so all these 3 techniques are very useful in analytical chemistry. Here is how we do titrations. The basic setup is the same, okay? So which means that you add something from a burette to a flask. You keep adding until you reach what is called an endpoint, okay? So there are different ways of doing this. So for example, for a precipitation reaction, you're looking for precipitation over here, and until you don't see any more precipitation, you keep doing the titration. Those are the hardest ones to do because how do you know when the precipitate is completely formed? So sometimes those are a little bit more challenging. Acid-base titrations are really quite good because for acid-base you can use an indicator and that will tell you, oh look, there's a color change, okay, and therefore your titration is done. There are 2 points that we actually look for in titration. One is called the endpoint and the other one is called the equivalence point. Equivalence point is the molar ratio, okay, so when molar ratio is the same for whatever is in the burette and whatever is in the flask, that is called the equivalent point. End point is when the titration is stopped due to the color change in the indicator. Okay, so those 2 are not the same. In some cases, they may be the same, all right? And that is something you will learn more in Gen Chem 2 when they are the same and when they are not the same. So in what we will be doing in our labs and our studies right now, our endpoint and equivalence point are the same, okay? But when you get to a little bit more variety of reactions, then sometimes they are not the same, okay? And then again, indicator is used to tell if a reaction is over or not. And this is really useful when you're titrating two substances that are clear and colorless, okay? And so there is no color change going on. The one other thing that I want to mention here before I go forward is standardization. And standardization is when you try to figure out the exact concentration of a solution. So, which means that you have to have at least one solution that you know the concentration of, and then the other one that you're trying to figure out, okay? And that is standardization. You will do everything in the lab, by the way. You'll do standardization, you will do acid base, oxidation, reduction, titrations, okay, in the lab. So you'll get an idea of how these things are done practically. This is gravimetric analysis, and these are slightly different because it's not titration based. In these cases, these are all precipitation reactions. So once you do a precipitation reaction like this, where you have a solution that you're adding to another solution, and you form a precipitate, then you isolate the precipitate, okay, by doing a filtration. Once you filter the precipitate out, then you weigh it, okay? So you dry it and you weigh it, and then you do a back calculation, okay, to figure out how much of the initial substance was in there. So usually crucibles are used in this, and in some cases you actually use filter paper, and then you burn the filter paper and you just get the solid, okay, in there. So there are different ways of doing gravimetric analysis. Let's work on some calculations using stoichiometry. We'll start with the simplest one, and then we'll take an example of each kind, okay, in there. So first one is find the concentration of all species in a 0.25 molar solution of magnesium chloride. It seems such a simple problem and you don't even know where to begin. And so since you're asked the concentration of all species in the solution, you find out what all the species are, which means you write the dissociation equation, which is magnesium chloride to give magnesium ions and then 2 chloride ions. And remember again from our balancing equations and all that good stuff, that Cl2 is not Cl2 as in molecular chlorine. It's actually 2 chloride ions that are associated with every single magnesium. So that you have 2 chloride ions over here in solution. So which means that if magnesium chloride solution was 0.25 molar, the ratio of magnesium ions in there is 1:1, which means that if magnesium chloride solution is 1 molar, then the concentration of magnesium ions is also 0.25 molar. If the concentration of magnesium chloride is 0.25 molar, 2 chloride ions will have double that amount, because here the molar ratio is 1:2, and so it ends up happening like it's 0.50 molar of chloride ions. It might seem a little weird to you. You might think that how is the concentration changed? It's not changed. It's still the same. But the thing is that the number of chloride ions you have in there are double than what magnesium ions are in there. So keep it simple. All right, next problem. A soluble silver compound was analyzed for the percent of silver by adding sodium chloride solution to the precipitate, and the silver ion is precipitated then as silver chloride. If 1.583 grams of silver compound gave 1.788 grams of silver chloride, what is the mass percent of silver in the compound? Okay, so let's look at this problem. All right, it is a precipitation equation. It's a precipitation reaction, and you are forming the product that's being formed is 1.788 grams, okay? The initial compound was 1.588. We are not told how much sodium chloride is being added, so which means that it is not part of the equation. We don't have to worry about it, okay? All we need are these two numbers to work with, which 1.583 of any silver compound, we don't even know what that is, okay? So which means that we have to start with 1.788 grams of silver chloride. So once you start with that, then you work your way to figure out the mass percent of the silver in the compound, okay? So our strategy is going to be that we take the 1.788 grams of silver chloride, convert it into moles. Remember, in stoichiometry, everything is moles. So you convert that into moles in 1 mole of silver chloride, how many moles of silver do you have? This is kind of the same question as what we did before. So you really need to know the formulas of all these things. So silver 1 chloride is, of course, 1:1 ratio. And then from moles of silver, you will convert it into grams of silver. Once we have the grams of silver, then our last calculation is going to be the percent of silver using this number, okay, that we have. So let's set it up. To find the moles of AgCl, of silver chloride, you need to know the molar mass of silver chloride. So this is our setup, 1.788 grams of silver chloride. You find the moles of silver chloride using the molar mass. In 1 mole of silver chloride, there is 1 mole of silver. You convert those moles of silver to grams of silver, okay? See, over here, we don't really need sodium chloride at all for anything. It's just an information that's given to you as to what is being used to precipitate silver chloride, but otherwise it's not really required in the problem solving. So then we have 1.346 grams of silver in the compound, okay, because that is how much silver has precipitated out. So if this is the amount of silver you have in the compound, then here is the initial compound, you find the percent, okay, of silver in there. Now remember, a quick cross-check is that the amount of silver you have in the compound should be less than the compound, okay, that you started with. If it is more than that, then obviously you did something wrong, okay? So that's a quick check to see if your answer is correct or not. So the mass percent then is the amount of silver that you calculated over the mass of the original compound, and it gives you the mass percent of silver. Another problem, zinc sulfide reacts with hydrochloric acid to produce hydrogen sulfide gas. Okay, and here's the equation given to you. The question is, how many milliliters of 0.0512 molar of HCl are required to react with 0.392 grams of zinc sulfide? This is a typical stoichiometric problem for solutions, and in this case, you have one solid and one solution, okay? So for one solid, you're given grams. For the other solution, you're given the molarity, okay, which is 0.0512 moles per liters, okay, of HCl. And the equation is given to us. First of all, make sure that your equation is balanced, which it is, okay, over here. So then let's form our strategy, okay? So our strategy, or the question is, how many milliliters of 0.0512 molar HCl? So if we are trying to find out how many milliliters or how much volume of HCl we need, we can't start with this. We have to start with then the zinc sulfide, okay? So grams of zinc sulfide, convert that into moles as usual. Then you find the moles of HCl that will be required, and this is going to come from the balanced equation as usual. And then from the moles of HCl, you find the volume of HCl. And how do you find this? You use the molarity, okay, that is given to us to find the volume of HCl used. So that is our strategy. Let's start working. The molar mass to find the moles of zinc sulfide. This is the molar mass, 1 zinc plus 1 sulfide, 1 sulfur. So first, you convert the grams of zinc sulfide into moles of zinc sulfide using the molar mass. Then using the balanced equation, you find out the moles of HCl, which is 2:1 ratio from the equation. Once you found the moles of HCl, then you convert the moles of HCl into liters of solution that you would need. Okay, and this is molarity, 0.512 moles per liter. Remember, we have just inversed it, okay, because this is the quantity that we need. Okay, we need to find the molarity of the solution. We need to find the volume of the solution. So that's why we need to inverse molarity over here. Okay, and so then our final answer is 0.157 liters, which is 157 milliliters of HCl solution. So what does this mean now for us? It means that to completely react 0.392 grams of zinc sulfide, you need 157 milliliters of 0.0512 molar HCl. In mass stoichiometries in chapter 3, we were trying to do the same thing but with grams. Now we're working with molarity. Okay, so you have to work with volume and then the molarities here. Another problem. We have a solution of hydrogen peroxide, okay, which is sold in drugstores. And we're trying to analyze how much hydrogen peroxide is there by titrating it with potassium permanganate. This is actually a redox titration. We don't have enough information yet to make that judgment, but still, I'm telling you, okay, that this is actually an oxidation reduction titration, all right, that is being set up. And so the question then is, what is the mass percent of H2O2 in a solution if 57.5 grams of the hydrogen peroxide solution required 38.9 milliliters of 0.53 molar potassium permanganate for its titration, okay? So we are trying to figure out the mass percent of peroxide in the original solution, okay, that we started with. And how much of that solution do we have? We have 57.5 grams of that solution. This is another classic stoichiometric problem. In the previous one, we were dealing with grams, okay, to begin with. We had grams of zinc sulfide that we started with. Now we actually are starting with a solution, okay, over here. So if you're starting with a solution, then you have to find moles, okay, from this solution. Let's look at the equation. This is a balanced equation already given to us. And what is necessary over here is, of course, the mole ratio of hydrogen peroxide to KMnO4. Everything else that is in the equation is just to write the products out and to balance out the equation. But our main stoichiometry is right over here, okay? So 38.9 milliliters of 0.53 molar KMnO4 is required, all right, for the titration. So that's what you start with, okay? So our strategy is first to find the moles of potassium permanganate. From the moles of KMnO4, we will find the moles of peroxide, again using the equation. Then we find the mass of peroxide, which is just converting the moles into the grams. And then we find the percent, okay, of peroxide. So simple and straightforward, okay, and keep it that way too. Always have a strategy in mind, okay, before you start working a problem, because if you start setting up a problem without a strategy, okay, then you might get lost, okay. Eventually, you may not need that strategy anymore, but initially, I think you should write it out. So molar mass of H2O2, hydrogen peroxide, we need this. We do not need the molar mass of KMnO4 because the molarity is given to us. And if we have the molarity and the volume, we can find the moles of KMnO4 from right here. Okay, so the moles of KMnO4 are actually coming from the concentration, so we do not need the mass of potassium permanganate. So here is how we calculate the moles of potassium permanganate is you start with the volume. Again, remember you have to convert the milliliters into liters because you're multiplying it by the molarity. So molarity is moles per liter. So you need to convert milliliters to liters, which is 38.9 times 10 to the negative 3 liters. Once you find the moles, which is volume times molarity gives the moles, then you do the mole ratio here. We're converting now in our second step to the moles of H2O2. So 5 moles of peroxide to 2 moles of KMnO4 coming from the balanced equation. And then you find the mass of hydrogen peroxide by multiplying the moles of peroxide with the mass. Okay, so that's this unit conversion there. And you get 1.77 grams of peroxide. So which means this titration gave us 1.77 grams of peroxide in the solution. We started with 57.5 grams of solution. So then to find the mass percent, okay, we need to take this number divided by the grams of solution in there. And here's our beautiful answer. We have 3.07% of hydrogen peroxide in this solution. Okay, so another great stoichiometric problem, okay, which involves molarity. The next couple problems that we have are for acid-base titration. We have done precipitation, we have done redox, and so now the only thing that is remaining is acid-base, okay? So let's see what we have. A student measured exactly 15.0 milliliters of an unknown monoprotic acid, placed it in an Erlenmeyer flask, added the indicator, did the titration, and at the end, the student had added 35.0 milliliters of 0.12 molar sodium hydroxide to neutralize the acid. Calculate the molarity of the acid. Okay, let's analyze the problem before we start approaching anything at all. Let's look at the data that's given to us. First of all, if you see, there are no grams given over here. Okay, and the grams is only when you have any kind of course, mass. Okay, but we have solutions given here. So which means we have two solutions, an acidic solution and a basic solution. So no grams required over here. So that's the first observation, which means that we have to get our molarity or our moles from the molarity, okay, that's given to us. And we're actually trying to find the molarity of the other substance. Okay, so let's look at that for just a second. We have an unknown monoprotic acid, okay, solution. This is an important part right here, monoprotic acid, okay, because the monoprotic acid is reacting with sodium hydroxide. And if you think back to the acid-base reactions that we wrote out, you need one H plus to react with one hydroxide to give water. Okay, those are your traditional acid-base reactions. So monoprotic meaning that you have one proton to give, and sodium hydroxide has one hydroxide to give, which means that the molar ratio here is 1:1. We don't know what the unknown acid is. Okay, that's the thing. The only thing we know is that it is monoprotic, and that is an important part because in any stoichiometry you need to know the mole ratio. All right, so the monoprotic here tells us that the mole ratio is going to be 1:1. If this was diprotic, then it would be 2:1. Okay, because then you would need 2 of the sodium hydroxide for every one of the diprotic acid, if this was a diprotic acid. Okay, but this is monoprotic, so we need 1:1 ratio. Okay, so now let's develop our strategy first. Okay, we have the volume and molarity of sodium hydroxide given to us. So we will find moles of sodium hydroxide using the molarity and volume of sodium hydroxide. Then we will find the moles of acid from the equation which I just told you is 1:1, okay, coming from the monoprotic acid. And from the moles of acid, then we'll find the molarity, and the molarity is from the volume also, okay, that is given to us. So here is our setup. The liters here, this is 0.035 liters coming from the 35 milliliters, so you converted that into liters, and liters times molarity will give us the moles of sodium hydroxide, so that's what this is. And then we have the 1 mole of acid to base ratio, and this is coming from the fact that this is a monoprotic acid, or monoprotic acid. And so this gives us 0.042 moles of the acid. You can continue on over here also and divide it by the volume, or you can do it separately because now you have the moles. To find the molarity, you need to have moles over liters. So the moles you just calculated, the liters are given to you in the problem. So 15 milliliter, make sure you convert that into liters because molarity is moles over liters. And so your concentration of the unknown acid is 0.28 molar. Okay, solution. So that is how you would set this problem up. Let's take another one. Calculate the molarity of a 25 milliliters of a monoprotic acid if it took 45.50 milliliters of 0.25 molar KOH, potassium hydroxide, to neutralize the acid. It's kind of similar to what we had over here. So in this case, again, we have monoprotic acid and then again, one of the hydroxide. So our mole ratio is going to be 1:1. We will start again by finding the moles of the potassium hydroxide, which is right here. So moles, which is this is the molarity of KOH times the liters of KOH gives us the moles of potassium hydroxide. Find the moles of the acid by doing the mole ratio, which is this much of acid then, and divide that quantity by the volume of the acid. That gives you the molarity of the acid. Okay, so keep it simple. Now in these cases the mole ratio was 1:1, but that may not always be the case, so make sure that you read the question carefully, and if an equation is given to you, make sure it's balanced and you use the mole ratio. Your keywords and concepts for this chapter, definitely you should know molarity, because if you don't know molarity, then how are you going to do the stoichiometry? So make sure you know the molarity. The solution stoichiometry comprises of two main titrations that you did, which is volumetric titration. And in this case of titration, you can actually have precipitation, acid base, redox, all different kinds of titrations. So you just have to kind of read the question carefully and then take from there as to what are you trying to solve. Okay, and so you should know the two keywords, endpoint and equivalent point. Um, and then gravimetric analysis is when you're dealing with pretty much precipitation reactions. Okay, volumetric analysis could be for anything. Gravimetric is specifically for precipitation reactions. But anyhow, the basic concept of stoichiometry is the same. Please practice, practice, practice.